Hello, today we're going to discuss natural selection. Alright, so what is natural selection? It is the process whereby organisms better adapted to their environment tend to survive and produce more offspring. So as we can see in the GIF above, the green beetles blend in more to the green plant they're on, and the brown beetles, so they are more likely to survive. Those green beetles would be more likely to produce since they survived, and they're likely to make even more green beetles. So again, it's over generations of time you see natural selection happen. It's not just, immediately changing within that certain lifetime. It's about how the inheritance of better genes, or better genes for survival, tends to last longer throughout many generations. You can see that in the picture in the top right too. Depending on the situation, a certain beak size in different pinches, that's specifically what Charles Darwin studied, could be more advantageous or not, depending on what their diet or what kind of seeds they consumed. Okay, so there are three different kinds of shifts of natural selection: directional, stabilizing, and disruptive. We're going to talk about all of them. But first, the easiest way to understand and see these shifts is by using a bell curve. Okay, so a bell curve basically shows that there is the most of something in the middle or the average, while there is the least towards the outsides. That's what a bell curve initially shows. So if you have the y-axis being just the number of individuals per trait, that again makes sense with the most being in the middle. And then the quantification of trait, that is going to be the x-axis. So basically, you're going to want to think of whatever trait it is you're studying or looking at as a spectrum across the bottom, with one end of that spectrum being on the left, the other end being on the right, and then some kind of intermediate in the middle. Most common thing would be like having, for color, you have white on one end of the spectrum, black on the other end of the spectrum, and then gray in kind of that intermediate. So that's just a very basic example. And we'll get into some more examples. So first, directional selection. Okay, so this is where you have a shift towards one end of the spectrum over many generations or towards the other end. So going, I guess, from intermediate more to one side or the other. You can see that in the image with the dashed line being the original population and the shift over with the solid line. An example of that would be light-colored peppered moths are better camouflaged against a pristine environment. Likewise, dark colored peppered moths are better camouflaged against a sooty environment. This was a big thing in the Industrial Revolution, when there was a lot of soot from that pollution basically produced in the air. So basically, these moths would shift towards being darker if there was in a highly populated highly polluted soot environment where the trees are mostly black, because then you can blend in and be less likely to be eaten. Or you could have a shift more towards the right if there was less pollution in an area, and it would better match with the white already bark of the trees that were natural. Next one is stabilizing selection. So this is where you have the intermediate increase in population most, while the kind of outside end of the spectrum decrease even more. So example of this is robins typically lay 4 eggs, an example of stabilizing selection. Larger clutches may result in malnourished chicks, while smaller clutches may result in no viable offspring. So basically 4 is just the right amount to be able to properly feed them and nourish them. If you had too many, they might not be able to be nourished. If there was not enough, those baby robins could be eaten by a predator or something, and then you wouldn't have any offspring to actually carry on the population. So 4 is just the right amount of eggs for robins. So you can see on that image on the left how you kind of have an end of the spectrum, so a low number like 1 versus a high number like 7, and 4 kind of falls right in the middle there, has the perfect amount, so that population is going to increase, or sorry, let me say this, that trait is going to increase in likelihood because it is advantageous. Last kind of curve is disruptive selection. Okay, so this is where basically it's the opposite of stabilizing selection. Both the outsides of the or the outer ends of the spectrum increase in population or likelihood, while the intermediate decreases. You can see in shell color potentially of clams. Say for example, if you're an intermediate color, you could be seen in both a brown environment and a white or light environment, while as if you were one color or the other, you could completely blend into one environment. So if you can be seen in both, you would be more likely to be eaten or consumed by a predator, whereas if you're one color completely, you could better camouflage into one whole environment and be more likely to survive, reproduce. That same trait carries on to the next generation, and so on and so on and so on. All right, so all of those curves and shifts completely depend on the situation and the context of the environment and what species you're talking about. But now we're going to talk about other kinds of selection. Okay, so there is sexual selection and there is artificial selection. Now, sexual selection still happens naturally, but it can have any of the curves or shifts below. And you can see there, as an example, they're using lemurs and fur color. So, again, completely depending on the situation, the environment, the context, any of those shifts can happen, and that can happen with sexual selection and artificial selection. Artificial selection is the only one that's not natural, but we're going to talk about sexual selection first. Okay, so examples of sexual selection. So, what's interesting about sexual selection is basically whatever trait is sexually more attractive to that of the species. Obviously, that is going to be the one that is wanted to be reproduced with, and then that carries on to the next generation, and so on and so on and so on, as whatever is more attractive. Now, the particular thing that's interesting about this is it's not necessarily best for survival, this trait. For example, peacock feathers. So if you have bigger, more beautiful looking feathers on a male peacock, you're going to be more likely to mate, right? But the thing is that with longer feathers, that's more weight, more drag, or not as fast. You can't really fly as far, if at all. So it's a real actual hindrance for like physical survival against predators, but it still exists and is so prominent because life is about reproduction. So ultimately, it could be a hindrance to your physical survival, but if you're able to at least survive to that reproduction point where you can produce some kind of offspring, that's really what matters the most. Sometimes, though, it can actually coincide with one another. For example, with deer or elk, if you have bigger antlers, that's going to be more attractive, and you're going to also be a better fighter. Female elk or deer that are nearby and see basically a fight between two males, they're going to find the more attractive male with the bigger antlers, the better fighter, to be the one that they reproduce with. And then you just have other things as well. For example, with spiders, they often do mating dances, so whichever dance is deemed most attractive is the kind of spider that's going to be mated with. You see this also with frogs, like whichever croak sounds the prettiest, bird song, same thing. So just a whole nother dynamic to throw into just simply survival to the reproduction point. That's really the main thing. All right, artificial selection is selection that is done exclusively by humans because we are specifically choosing which organisms are breeding with one another to try and get the traits that we want the most. Most common example is, for example, with wolves and tigers, so basically big dogs, big cats. Humans bred the traits that they wanted, so the kind of wolves and cats that were the most disciplined, the most friendly, the easiest to train. So those traits, so they would take a wolf, big cat, that was the easiest to train, friendly, disciplined, breed it with another wolf or big cat that was also the same way, and you'll end up getting puppies, kittens that are likely to be the same way, and then you keep breeding in that same process again and again and again until you end up getting a whole new species that is completely what your desired trait is, such as dogs and cats. So not aggressive, not predators, just friendly companions. So that's how we get dogs and cats. It's from selectively breeding wolves, big cats, to be what we want. And then this is still actually done today with, for example, like horses. So a lot of people bet on horse races as to which is the faster horse. If you breed a fast horse with another fast horse, the offspring of those two horses is also likely to be fast or even potentially faster. So that is how, you can just keep selectively breeding for what you want. Thank you for watching. Please share and subscribe, and remember to spread kindness.